Hello and welcome. So in this video we're going to do some fractional calculus. Particularly we're going to talk about how to differentiate a function for a fractional number of times. For instance, how to find the 2.5 order derivative of a function f of x. And as an application for that, we're going to see how to find the factorial of a fractional number. For instance, how to find 2.5 factorial. Now to start, we need to introduce the definition of an eigenfunction of an operator. For example, if we have an operator t, then a function x of t is called the eigenfunction of this operator t if the result of applying this function to this operator was x of t itself, or at least a scalar version of it. So lambda is just a scalar value. So x of t is called the eigenfunction of this operator if this equation was satisfied, and lambda is called the eigenvalue. Now in matrices, if we consider a matrix A, then a vector v is called eigenvector of this matrix if the result of multiplying this matrix by this vector to transform it into another vector is v itself, or a scalar version of it. So lambda is called the eigenvalue and v is called the eigenvector. Now if we took the differentiation as an operator, then the question is, what is the eigenfunction of the differentiation? In other words, what is the function that has a derivative equal to the function itself? The obvious answer is e to x. If you differentiate e to x, you're going to get e to x again, even if you differentiate it n times. Now we can write a more general statement. If we have the derivative of e to ax, then the result is a e to ax. If we differentiate it again, so d by dx, a times e to ax, we're going to get a squared e to ax, which equals to the second derivative of e to ax. Now, a more general statement is the nth derivative of e to ax, which is obviously equal to a raised to a power of n times e to ax. Actually, this is true for all n values, even fractional ones. For instance, if we have the 0.5 order derivative of e to ax, then the result is, and according to this formula, is a raised to a power of n, which is equal to the order of the differentiation, which is 0.5 in our case, so a raised to a power of 0.5 e to ax, which is equal to square root of a times e to ax. Now if we took the 0.5 order derivative of this again, what are we going to get? So 0.5 order derivative of square root of a times e to ax is, square root of a is just a constant, and the 0.5 order derivative of e to ax is again square root of a times e to ax, as here. So the result is a e to ax, which is the first derivative of e to ax, since 0.5 plus 0.5 is 1. Just like how we obtain the second order derivative of a function by applying a first order derivative 2 times. Now this is strictly true for exponentials, since they act as the eigenfunctions of the differentiation. Now what about other functions? Polynomials, trigonometrics, hyperbolic functions, and logarithmic functions. Now a simple trick to solve this problem is to rewrite other functions in terms of exponentials. For instance, if you want to find the 0.6 order derivative of sine x, then you're going to do that by first rewriting the sine x in terms of exponentials. So we get e to jx minus e to minus jx divided by 2. So the result now can be obviously written as j raised to a power of 0.6 e to jx minus j raised to a power of 0.6 e to minus jx divided by 2. So this is this 0.6 order derivative of sine x. Now I bet if you took the 0.4 derivative of this thing, then you're gonna get the first derivative of sine x, which is cosine x. You can check that. Now, what about other functions? How to find a fractional order derivative of an arbitrary function f of x? Well, luckily we have the Fourier transform, a tool that is just designed to analyze the signal or rewrite signal in terms of complex exponentials. I have talked about Fourier transform for about an hour in details in one of my videos. You are recommended to watch that video. The link is available in the description section down below. You can check it later. Now I'm going to assume that you watched that video. So I'm going to write that f of t can be rewritten as the inverse Fourier transform of its forward Fourier transform. So differentiating a function for n times is corresponded to taking the nth derivative of f of f e to j omega t dt. Now f of f is a constant with respect to this differentiation. So we have f of f and the nth derivative of e to j omega t is j omega raised to a power of n e to j omega t dt. So we can say that the nth derivative, sorry, I think I made some mistakes with the variable. This is t not x. So the nth derivative of f of t can be rewritten as the inverse Fourier transform of f of f multiplied by j omega raised to a power of n, where n can take any fractional number. Now, as I promised in the beginning, we're going to see how to find 2.5 factorial. The idea is to differentiate t raised to a power of n times. For instance, if you want to find 3 factorial, all you need to do is to differentiate t raised to a power of a 3 times. So the first derivative is 3 times t squared, and the second derivative is 6 times t, and the third derivative is 6, which is 3 factorial. So to find 2.5 factorial, all we need to do is to differentiate t raised to a power of 2.5 times. Now, to do this, we're going to use the trick of the Fourier transform for this function, t raised to a power of 2.5. Unfortunately, the Fourier transform of t raised to a power of n in general is not defined, because t raised to a power of n is not a square integrable function, doesn't have finite energy, which is a sufficient condition for the Fourier transform to exist. So I'm going to use the Laplace transform instead. The Laplace transform has a similar definition to the Fourier transform. This is the inverse formula. So you can notice that it also rewrites the function in terms of exponentials. So The Laplace transform of t raised to the power of 2.5 is defined as integration from 0 to infinity t raised to the power of 2.5 times e to minus st dt. And differentiating t raised to the power of 2.5 times is equivalent to multiplying the transform in s raised to the power of 2.5. Now the transform is this again. Now we know that the result of differentiating this function 2.5 times is going to be 2.5 factorial, which is a constant, which we know that it has a Laplace transform of 2.5 factorial over s. So this integral should be equal to this. So we can write that 2.5 factorial over s is equal to s raised to the power of 2.5 integration from 0 to infinity t raised to 2.5 e to minus st dt. Now I only need the value of 2.5 factorial. So I'm going to substitute s equal 1 to get this value. So this means that 2.5 factorial equal to s raised 1 raised to the power 2.5 is 1 again, and integration t to a power of 2.5 e to minus st is going to be e to minus t when s equal 1 dt. So that's it. That's how to find 2.5 factorial. Now in general we can write a general formula to find the n factorial, where n is a fractional number, according to what we earlier said, can be written as integration t to power n e to minus t dt, which is called the generalized factorial function. Actually, this definition is closely related to the gamma function. Gamma function is defined as gamma of x equal to integration t to raise to a power of x minus 1 e to minus t dt. So you can see that they have a similar definition. Now, as a summary, we can say that the idea of the eigenfunctions of operators is very popular in fractional calculus. One more interesting application of this idea is in finding the fractional Fourier transform. Actually, the Fourier transform of e to minus pi t square, a Gaussian function, is equal to e to minus pi f square, which is the function itself in the frequency domain. So it's obvious that the Gaussian act as a eigenfunction of the Fourier transform. In fact, if we took the nth order Fourier transform, we're going to obtain a scaled version of e to minus pi f square, where lambda is the eigenvalue. So if we want to find, for example, the 0.5 order Fourier transform of a function f of x, all we need to do is to rewrite the function f of x, which is an arbitrary function, in terms of Gaussians, which is exactly what the Hermite transform does. Now, the Fourier transform, we took one more 0.5 order Fourier transform of this. We're going to get first order Fourier transform of f of x, as we said earlier. Now that's it for now. I'm going to talk about this in more details in the upcoming videos. Thanks for watching.